Inside every single microchip, there's an invisible, high stakes race happening billions of times a second. Signals are just sprinting through these microscopic mazes of logic gates. And if even one of those signals shows up a fraction of a second too late, or hey, even too early, the whole system can just crash. Today, we're going to pull back the curtain on how engineers actually win this impossible race every single time through a critical process called AC timing closure. So here's the plan. We'll start by really understanding the race itself. Then we'll meet the automated timekeeper that kind of governs it all. We'll see how the rules get set, how every single path is analyzed, and finally, how engineers fix the inevitable traffic jams to get that chip across the finish line. All right, let's just get into it. Think about the scale of this problem for a second. You're trying to get billions, sometimes even trillions, of signals to all arrive at their destinations, perfectly synchronized on a tiny piece of silicon smaller than your fingernail. The scale is it's absolutely mind-boggling. So what do they have in common? Well, it turns out pretty much everything. Just picture it. Every signal is a runner, and every logic gate is a checkpoint. The data itself, that's the baton they're passing. For the whole thing to work, every single handoff has to be timed to utter perfection. A dropped baton, a runner leaving the block just a split second too early, the whole team is out. It's the exact same idea here. And that brings us right to the heart of the problem, what we call a timing violation. Now, here's the thing that might seem a little weird. In a chip, being too early is just as bad as being too late. The whole system relies on this incredibly precise, predictable rhythm. Any signal that breaks that rhythm can corrupt the data and cause a total system failure. This slide here just breaks it down perfectly. There are two cardinal sins. The first is a setup violation. Think of it like being late for your train. The doors have already closed, you missed it. The other is a hold violation. That's like jumping off the train before it's even stopped. You left the station too early. In both cases, you've got chaos. And on a chip, chaos means bad data. So you've got billions of these paths. How in the world could a person possibly check them all by hand? Well, the honest answer is, you can't. It's just not physically possible. And that's exactly where our solution comes in. So let's meet the automated timekeeper that acts as the referee for this whole incredible race. The whole process is called static timing analysis, or STA for short. Now, instead of trying to simulate every possible thing that could ever happen on the chip, a task that would literally take forever, STA uses these really sophisticated mathematical models to calculate the delay of every single path. The key here is that it's exhaustive, it checks everything, and it's fast. It's really the only way to verify a modern, complex chip design. And the go-to tool for this massive job, the undisputed gold standard in the industry, is a piece of software from Synopsys called PrimeTime. For chip designers, this tool is basically the ultimate authority on timing. It's the referee that calls out every single violation of the rules we've been talking about. So engineers follow a really structured workflow inside a tool like this. First up, they load the chip's blueprint. That's called a netlist, along with all the specs for every little component. Then, and this is key, they define the rules of the race, things like clock speeds. After that, they hit go and run the analysis. Then comes the detective work, digging into the results to figure out why things are failing. And finally, the most important part, they actually fix the problems. Okay, so let's talk about that step, setting the rules. Because before any analysis can even happen, engineers have to tell the tool exactly what the rules of the race are. They have to set the stage for the entire competition. And it all begins with the clock. The clock is the heartbeat of the chip. It's the starting pistol for every single race. So engineers have to define its speed with incredible precision because that number sets the time budget for every single path. If you get that wrong, the whole analysis is basically worthless. Next up, you have to define the environment the chip is going to live in. A chip that's running in a nice, cool server farm behaves totally differently than one inside a hot smartphone in your pocket in the middle of summer. These conditions, we call them process voltage and temperature, or PVT, they're absolutely critical because they directly change how fast signals travel. The analysis has to make sure the chip works perfectly at all of these extremes. And here's where the complexity just goes through the roof. Even on what looks like a single perfect chip, there are these microscopic manufacturing variations. It means some logic gates are just a tiny bit faster or slower than their neighbors. This is called on-chip variation. So to guarantee the chip will work, engineers have to add what they call a pessimism factor to their analysis, basically building in a safety margin to account for this reality.
All right, the rules are set, the environment's defined, the safety margins are in place. Now it is time to run the analysis and see who's breaking the rules. Let the race begin.
The first report an engineer checks usually isn't about tiny nanosecond violations. It's about much bigger structural problems. The tool can run these high-level sanity checks that immediately flag fundamental issues. Like you can see here, the tool found a bunch of components that aren't even connected to a clock. I mean, you have to fix these big problems first before you can even think about the small ones.
So once those basic checks are clean, then engineers can dive into the real failing paths. The tool has this amazing feature called the Path Inspector, which is like a high-powered microscope. It lets an engineer zoom right in on one single failing path and see a detailed breakdown of its total delay piece by piece. You can see exactly how much time was spent in every single logic gate and wire along the way.
And this isn't just about staring at tables of numbers, not at all. Debugging timing is an intensely visual process. The tool gives you all sorts of ways to visualize the data, from high-level charts that show you where the biggest problem areas are, to these detailed clock graphs that let you trace the clock's journey through the chip. It helps you see both the forest and the trees. So we found the late signals, we found the early ones. We know exactly where the traffic jams are. Now for the most important part, actually fixing them and getting our design across that finish line.
This whole process of making these targeted fixes late in the design cycle is called an engineering change order, or ECO for short. And you can really think of it like performing microscopic surgery on the chip's blueprint. You're altering very specific signal paths without having to go back and redesign the whole chip. It's precise, it's efficient, and it's absolutely essential.
So what does this microscopic surgery actually look like? Well, there are a few go-to moves. A really common one is to size up a cell. That just means swapping out a standard logic gate for a more powerful, faster version. Another one is to insert a buffer, which is kind of like adding a booster station to a long wire to keep the signal strong. Sometimes engineers might even physically move wires farther apart to cut down on electrical interference. The goal of all this work, the analysis, the debugging, the surgical fixes, is to achieve what the industry calls timing closure. And this is the moment of victory. It means every single one of those billions of paths meets its timing goals under all the different conditions with all the safety margins baked in. It is the final sign-off, it is the green light to send the design to the factory. But here's the thing. As we pack more and more transistors onto chips, we're not just talking billions anymore, we're talking trillions. The number of paths to check becomes almost infinite. The challenge of finding and fixing every violation is growing exponentially, and this has kicked off a massive trend toward using AI and machine learning to try and automate this process. But will these new AI tools be enough to keep up? That is the billion-dollar question that the entire industry is trying to answer right now.